So there are actually two topics in this next section. 7.4, I believe, is in our textbook. It's both arc length and surface area are both covered in the same section. The good news is this section is not, in my opinion, as challenging as the last two. The last two, when you were setting up the problems, you had to be super careful. You know, there were so many details you had to pay attention to when you're setting up the problems. Here, once we derive the formulas, you're going to see that the formulas are very straightforward to apply. They don't change that much when the rotations are on the x-axis or the y-axis. So in a sense, as one of my students in the previous semesters put it, this is like a section where you can rest your brain a little bit, because the next few sections, again, they're going to be a little bit more involved. Again, the derivation is involved, but once we get the formula, we're applying it. The setting up of the problems, hopefully, are not going to be that bad. First of all, arc length. The general idea is the same. We have a difficult question, in this case, finding the length of a curve. From college algebra, we know how to find the length of a straight line. A straight line, you know, you can use the Pythagorean theorem if you know the coordinates of the point. There is a very simple formula that gives you the distance between those 2 points. But what do you do with a curve? Something like this. Again, the curve given in red is our y equals f of x function here. So let's label that. So we have y equals f of x. That's the red curve here. How do we find the length of this curve? Well, we're going to go back to the general idea that we've used throughout this whole chapter, which is, if you have a difficult problem, first divide the problem into easier problems. So look at, basically look at this curve that is made out of n separate lines. So for example, you have, we've selected in the sample graph points p sub 0, p sub 1, all the way to p sub 9, and I've joined each adjacent point with a straight line. So I have something that looks like a polygon, and if we could add the lengths of these lines to each other, we're going to give it a pretty good approximation about what this curve's length is. But what do you want to do in the ultimate case, is you want to find the exact length of this curve. You don't want to have just 9 line segments, right? How many line segments would you like to have ideally? Infinitely many, right? So we have a difficult question, finding the length of a curve. We subdivide it into easier questions, which is finding the length of a straight line. We're going to do n of those, take a limit as n goes to infinity. We're going to have a formula in our hands. So let's see how we can find, first of all, the length of a straight line. Let's see, where was I? Okay, so the length of a straight line. So first of all, some notation. The distance between p sub 0 to p sub 1, I'm calling it delta s sub 1, etc. And in general, any distance between any 2 points, x sub I and x sub I minus 1, I'm calling it delta s sub I. So delta s is the length of a very small piece of this curve. And to make things a little bit easier for the rest of the problem, for the rest of the derivation, I dropped the subscript of I. But just imagine, everywhere you see an s, there's really s sub I here, just making this notation a little bit simpler for you to deal with. So what I have done is I've taken one little line from here. So say this line over here. I've taken this line, and I've enlarged it over here. Okay? So that line segment has been enlarged. This is the enlarged view, and I've broken down into its x and y components as delta x and delta y. And that line represents delta s, which is a small piece of this arc length s. Anytime we have a small piece, we usually put a delta in front of it. Okay. Now, first of all, we want to have an idea what delta s is in terms of delta x and delta y. So first of all, can you tell me what delta s squared is in this picture using the Pythagorean theorem? What is delta s squared? Yes, I want to go with Gracie's answer. Delta y squared is delta s. Exactly. By using the Pythagorean theorem, it is delta y quantity squared plus delta x quantity squared. The square of the hypotenuse is sum of the square of the legs. And now to find delta s, what should I be doing? Take the square root of both sides. So delta s is the square root of, by the way, in your handouts you have some blanks, so you can fill those blanks out as we're filling these in. So delta s can be written as the square root of delta y squared plus delta x squared. Now, usually when we integrate something, basically we already have an idea what the final answer will be. the final answer is you're going to add up infinitely many of those, so it's going to be something like integral of delta S. But usually, we don't have a ds in our problems. We either have a dx or a dy, right? So we should try to get rid of this ds, and we should try to end up with a dx or a dy. And the best way I can do that is, for example, let's say I want to end up with a dx. I don't want to end up with a ds. I want to end up with a dx. So to bring the x variable, what I'm going to do is I'm going to take the answer from the top and multiply it and divide it by delta x. Does this change the value of my expression? Absolutely not. We're multiplying it by 1, right? But this brought in that variable that I want, which is a delta x variable. The only problem is there's an extra delta x in the denominator. I want to keep the one on the top there, but the other one I want to kind of get rid of it. So how could I get rid of that delta x in the denominator? I'm going to put that under that square root sign. So I'm going to rewrite what delta s is under a big square root. On the outside, that one of the delta x's is staying on the outside. We still had delta y squared plus delta x squared over here. Okay. And on the bottom, okay, so this delta x that I have here in the denominator, how could you put that under a square root? This delta x that was in the denominator, how would you put it under the square root sign over here? What would it look like under the square root sign? Delta x squared, right? Because think about going backwards. When you take it out of the square root sign, it's going to lose its square. So that will come under the square root sign as delta x quantity squared. Now, if you simplify this a little bit, you can have delta y over delta x quantity squared. So let's just rewrite this expression. So delta s is equal to the square root of delta y over delta x. And I will combine them under 1 square plus what else should I have there? Plus 1, right? Because delta x squared over delta x squared, that is just 1. And on the outside, we have a delta x. So now I was able to get rid of the s variable in a sense, and I brought in the x and y variables. And I do have a delta x on the outside, so we're on the right track. Now, to find the exact area, what we should be doing is we should be adding n of those first, and we're going to take a limit as n goes to infinity. First, there's a question. Yes?
So where did the delta x come from? Why do you have to multiply?
Yes, because we're trying to end up with a dx in our integral. To end up with a dx, that's why we brought in the delta x variable. We multiply the top and the bottom by delta x, and you will see in the final formula that will give us a dx in our integral. So basically, we're applying a little trick there to bring in what we want. And by multiplying the top and the bottom by delta x, we didn't change the value of anything, so we could do that. So this was just one little interval there, one little line. Its length in terms of its x and y coordinates can be written like this. But we want n of those, right? So that's why I added n of those. And that's still an approximation. To get an exact answer, what should I be doing? Take a limit as n goes to infinity, right? And if I take a limit as n goes to infinity of the answer from the top, what would I get? Because delta s sub I, remember, this was what we call delta s. And I had dropped the subscript. So this is really our delta s sub I, basically. Okay. First of all, anytime you're trying to go limit as n goes to infinity, you can replace this part by what? The limit of a sum can be replaced by what? Which notation? The integral notation, right? So that is the integral notation. Okay, so we'll put the integral there. Now, instead of delta s sub I, let's look back up there what we got. We got the square root of delta y over delta x. But in the limiting case, we don't usually write delta. We usually write dy or dx, right, as n goes to infinity. So our delta x from here is going to be our dx. Now, what else should I have under the square root sign? This delta y over delta x, how could I write that one down? Remember, as the number of rectangles goes towards infinity, your delta y is becoming your dy, and your delta x is becoming your dx. That's the notation that we use under the integral sign. So what should I write under this integral then? Again, basically dy over dx squared plus 1. So I might write it like this, 1 plus dy over dx quantity squared. And over the given limits from a to b. So in general, this is the arc length formula that we're left with. We've already derived the first one. Take a look at what we have up there, integral of ds, where ds is basically square root of 1 plus dy over dx squared. But if you didn't multiply by delta x over delta x, if instead of that you multiply with delta y over delta y, you could have done the same manipulations, and guess what? You would have ended up with this formula down here. So instead of multiplying by delta x over delta x, if you multiply by delta y over delta y, then you're going to have this formula, which is basically another version of it. If your given function is x in terms of y, you would use that formula, because then you can differentiate x in terms of y. If your function is y in terms of x, then you would use the first formula. So this is the arc length formula. And let's do an example about arc length before we take a look at surface area. So let's fast forward to an arc length example. Let's do this example right here. Find the arc length of f of x equals x to the 3/2 over the interval from 0 to 4. I must tell you that the examples you will see in the textbook on arc length are very cooked up examples, because many times when you take the derivative of something and you square it and you put it under a square root sign, it becomes a very difficult function. It's very hard to integrate that. So they came up with these very interesting functions like x to the 3/2, or they have some very interesting ones. In general, when I give you a function to find the arc length, if the function is really difficult to integrate, I might actually tell you, set it up and use your graphing calculator to finish the problem. You will see that I have done that on several questions on your group activity. This one is not so bad. This one we can actually integrate, but don't be surprised if there are several examples on your textbook and group activity. It says just set it up and use your calculator. So this one we can actually do. Okay, the formula we just learned was arc length, again, usually is represented by lowercase s equals the integral of the square root of 1 plus dy dx quantity squared dx on the outside. In this case, limits are 0 to 4. And I must tell you that this formula only applies to smooth or differentiable curves. So, in the beginning, you may want to take a look at the graph of this function, what it looks like, that it doesn't have any sharp edges over the given interval. This one actually is a smooth curve. So let's just go ahead and find the arc length right away. So first step is to find dy dx. Dy dx, another way to write that would be f prime of x, right? Just the derivative of the given function. Okay, what is the derivative of f of x equals x to the 3/2? 3/2 times x to the 1/2, right? Because we're subtracting 1 from the power, right? So 3/2 times x to the 1/2. Then you want to square that. I'm going to do that as well over here before I put everything into my equation. Square that, you get 9/4 times what? If you square root x, because x to the 1/2 is root x, so if you square that, you end up with just an x. Right. Okay, so I did the preliminary work. I found dy dx squared. Now I'm going to put everything under that integral for the arc length. So s equals the integrals from 0 to 4 of the square root of 1 plus what I see in the formula dy dx squared, the derivative squared. I'm going to enter 9/4x. How could we integrate this one? Any suggestions? How about u sub, as Chris suggested? So let's go ahead and let u be equal to 1 plus 9/4x. Let u be equal to 1 plus 9/4x. Then du is 9/4 dx. And dx is the same as 4/9 times du. So I'll go back to this integral. For the square root, what should I be writing right now? The square root of u. And instead of dx, what should I be writing? Based on what I got down here, dx is 4/9 du. I'm going to pull the 4/9 outside and keep the du on the inside. Okay. We've got to be careful for these questions because in part of the process you're doing a differentiation. In the other part you're doing an integration. Like earlier we did the dy dx, we differentiated. Okay, now we're back to integration. We want to integrate u to the 1/2, which would be u to the 3/2 over 3/2 or times 2/3. And let's put the u back in there, u being 1 plus 9 over 4 times x. And limits are 0 to 4. If I plug in a 4, I'm going to get 1 plus 9 fourths times 4 just gives me a 9. So 1 plus 9 is 10. I also have a power of 3/2. Let me not forget that. So I'm plugging in a 4 for x. And what would that give you? Exactly, because the 4 and the 4 here, they cancel. You have 1 plus 9, 10. But don't forget the power. That is 10 to the 3/2, right? Now, usually when we plug in 0, we don't get anything. So we may sometimes get, ignore the 0. But in this case, if you plug in a 0, what do you get? 1 to the 3/2 or 1. So I can just subtract a 1 here. And this you can calculate with your graphing calculators or any type of calculator. 10 to the 3/2, you can easily enter it as 10 to the power of 1.5 if you need to. And if you simplify all of this, I believe you're going to get 9.07. Let me have somebody confirm that, please, by checking on the calculator. Okay, one more example on arc length. Sure, sure. Remember, we had to subtract because you plug in the upper limit minus you plug in the lower limit. The minus comes from plugging the lower limit, yes. Okay, here is another example. The function is ln of secant x. So the question is find the arc length of y equals ln of secant x over the interval from 0 to pi over 4. 0 to pi over 4. So once again, same formula, right? We're going to find arc length of a given function. The formula is very straightforward. It says we must find the integral of 1 plus dy dx quantity squared dx. This is what we're going to do for this problem. Yes, question? That's the other alternate form of the formula, the dx over dy squared and the dy on the outside. You would use that one if your given function is of the form x equals f of y. Say they give you x equals sine y, okay, something like that. Yes, these are very straightforward, right? You don't have to worry about what the graph looks like. The only thing is make sure that there are smooth curves, and usually if you're going to be able to apply the formula, they do give you smooth curves anyway, okay? So let's begin by differentiating y. So finding y prime or dy dx. Okay, what is the derivative of ln of secant x? First of all, ln of u, how do you differentiate ln u? 1 over u times u prime, right? So in this case, we're going to have 1 over secant x times the derivative of secant x, which is secant x times tangent x. We can't forget these important identities, guys, because they'll keep coming back. So secant of, derivative of secant is secant times tangent. That's because you had original function was ln of something, right? Right, so like ln of u, derivative is 1 over u times u prime, right? So again, this is kind of helping us remember a little bit about our differentiation skills. It's been a while since we've done that. Now, as you can see, the secants cancel, and we're left with tangent x. So dy dx is equal to tangent x. And remember, we're going to need to square it when we go inside that integral sign instead of square root sign. So I'm going to do that right in there. So to find the arc length from 0 to pi over 4, I need to integrate the square root of 1 plus dy dx squared. So what expression should I be entering under that square root sign? We already got dy dx is tangent x, right? Derivative of y with respect to x is tangent x. So you want to put the square of that quantity in the, because the formula calls for the square of that, right? So we want to put tangent square in there. How do we know, what do we know about this 1 plus tangent square quantity? Exactly. So that is the same as the square root of secant square x. And secant is positive in that interval. It can come out as positive secant x. And what do we know about the integral of secant x? Luckily, this was something you didn't have to memorize, but you should be able to get it when you need to. That was ln of secant plus tangent. So let me remind you, this was ln of secant plus tangent. We just have to worry about plugging the limits now. And the limits are 0 to pi over 4. Okay, secant of pi over 4. First, think about cosine of pi over 4, which is 1 over the square root of 2. Take the reciprocal of that. That will give me just radical 2. How about tangent of pi over 4? If pi over 4 or 45 degrees sine and cosine are equal, right? So what is tangent of pi over 4? Just 1. The ratio will be 1. Sine to cosine ratio will be 1. Tangent pi over 4 is 1. Now, ordinarily, you should also subtract what you get when you plug in the lower limit. Secant of 0, what is that? Think about cosine of 0. Cosine 0 is 1, and tangent 0 is 0. But that leads to nowhere because ln 1, after all, is still 0. So we can leave our answer as ln of, I can even drop the absolute values now because I know this quantity is positive anyway. So the answer is ln of radical 2 plus 1. And of course, you could get a decimal answer there, or you could leave the answer just like that. Okay. There's an example I want to be able to get to today, but just in case I don't get to it, I want to at least show you what it is, and maybe you can start working on it over the weekend, and you can ask me about it next time. And the example is, not that one, this one. Show that the circumference of a circle with radius r is the formula we well know, which is 2 pi r. Because that's, after all, an arc length, right? Basically, it's finding the arc length around a circle. So can we find these formulas we've been taking for granted up to now by using formulas from calculus, by using derivations from calculus? So hopefully we'll come back to it, but just in case we don't, I want to leave you with that. Okay, now let's go back to the surface area theory. So we can derive a formula there. 2 pi r was on the last slide, yes. Okay, surface area. Okay, first I'd like to do a demonstration actually. Let me go to my next one. That one. Okay. So just like the last two sections, in this section, we're going to find surface area of a solid of revolution. And to do that, we start with a function, say y equals f of x. We rotate it around the x-axis or the y-axis. Let's say that we rotate it around the x-axis for this example. So we're going to rotate it around the x-axis. This one's just a demo. Just look at it. We're going to derive the theory in a minute. But before we can rotate it around the x-axis, once again, we want to break the problem down into smaller and easier components. So we take that curve, and just like we did a few moments ago, we divide it into lines. So that curve, at the moment, is a union of finitely many lines. And of course, the more points you select along the curve, the better the approximation. At the moment, I only have 4 lines. But again, if I had, let's say, 25 lines, I could have a better approximation and less gaps between the line and the curve, etc. But at the moment, we have just 4 lines. I'm going to take each of those lines and rotate those around the x-axis. This is the graph that I would get. If I take each one of those lines and rotate around the x-axis, I get a solid. But that is not a perfect solid. It only used like 4 or 5, in this case, just 4 different solids. Ideally, I want to have n of those. As n goes to infinity, that's going to be the perfect solid generated. So once you do all that, you're going to end up with something like this. And our job is to find a formula that represents the volume of the solid generated. Okay? Now, what would you call each one of these structures? It's not a disk. It's not a shell. It's kind of a weird structure, right? It doesn't seem to have a very, immediate geometrical resemblance of an important figure that we know. But if you think about it this way, I'll just take one of these guys over here and turn it upside down so it sits on a circular end. This is actually called, this bottom figure here is called the frustum of a cone. So the top of the cone has been cut off and thrown away, so you just have the bottom, the base of the cone basically. And there's actually a formula for that. Okay, so again, we take a difficult question, we break it down into its sub-problems that are easier to handle. In this case, the sub-problem that's easier to handle is to find the surface area of the frustum of a cone. And from there, we're going to take a union of those to find the total volume of the entire surface area. Now, for that, I'm going to go back to my theory notes, and you should have a copy of this sheet that I'm about to go over with you. So once again, we take a curve, which is y equals f of x. In this case, this black, smooth curve. We rotate it around the x-axis, and we get this solid. The question is, what is the volume of the solid of revolution? Now, on that solid, I've shown you only one tiny little, some people call these bands, one tiny little frustum of a cone or a band. If we could find the surface area of that, the rest will be easy because we're just going to add up n of those and then take a limit as n goes to infinity. So first thing you need to know is what is the surface area for the frustum of a cone. And that I will just provide to you because we could go ahead and derive that as well. And if you're interested, please see me after class. I have a very nice book, Stewart, and they actually show the derivation of this particular formula. But at the moment, I'm just going to give it to you, and we'll use it in our derivation. So here's the formula from geometry that gives us the surface area for the frustum of a cone, which is 2 pi RL. You may wonder, what is R here and what is L here? Okay, 2 pi RL is the surface area of this frustum of a cone where the tip has been cut off of this cone. First of all, R is the average radius. So if you average the R sub 1 and R sub 2, R is considered to be the average radius. And what is L? L is basically the lateral side of this frustum of the cone. It's the lateral side of that figure. So we need to know this formula. S, the surface area for a frustum is 2 pi RL because our entire derivation will depend on that formula. 2 pi RL, where L is the lateral side. Okay, going back to that function that we were about to rotate, that little band there, we're going to first find the surface area for that one little band, and then add those up to find the total surface area. The function in black is y equals f of x. You know, the tiny little lateral side of that tiny little band, I call that delta s, a tiny little bit of arc length. I call that delta s. Now, from our previous work, we already know what delta s is, right? What is delta s from our previous work? And once again, I enlarged the figure over here for you. If you do the entire work like we did before, delta s, if you like, just watch this because we've just already done this anyway, and write the final results. Then you take square root of both sides, right? So delta s equals the square root of the right-hand side. And then what did we do? Does anybody remember? A minute ago, what did we do? We multiply and divide by delta x, right, to bring in the x variable. But just keep in mind that you could have just as easily multiply and divide by delta y to bring in dy if you wanted to do that. But just dx is fine for now. So if you do that, in a minute we're going to come back and simplify it. But remember from a little earlier that surface area for the frustum of a cone is 2 pi RL. For this figure, what is your r? What would r be for this figure? The radius of this frustum, the average radius. And keep in mind, these are getting so thin that the average radius is basically going to be like as if it's the radius of the whole thing. What is it going to be? Any suggestions? It depends on where you are, right? In general, what can you say that radius is going to be equal to? Y equals f of x, right? The radius, because it depends on where you are. If you are over here, you're going to have a bigger radius, right? And that is also going to be given by the function. Here it's a little bit higher because the function is higher. So if we go back here, remember the formula was 2 pi r L, right? 2 pi RL. Going back to that formula, 2 pi RL. So I have here 2 pi. Instead of the radius, I have f of x. And instead of L, the length of the lateral side, I have delta s. So this was replaced. Again, the general formula was 2 pi RL. This is my R, and this is my lateral side delta s. And from here, all we have to remember is we just know what delta s is, right? Let's put that in there. Delta s is delta x squared plus delta y squared. And, you know, let's just kind of fast forward the part where we multiply the top and bottom by delta x, and we put the delta x under the square root. What did we end up with when we did that? If you multiply the top and the bottom by delta x, we ended up with the square root of what? If you like, flip back to the previous page to let me know, what did we get there? 1 plus delta y over delta x, quantity squared, and on the outside, this is delta x. Okay. This is the surface area of a single frustum taken from that structure, taken from that solid. What do you really want to do ultimately? Again, to be more precise in my notation, I would have to put like delta x sub I, y sub I, because this is just one of them taken from the point I and I minus 1, let's say. But in the limiting case, you add n of them, you add infinitely many of them. And could somebody tell me what the formula will look like when you go to the integral? So again, we add those, and eventually you end up with the integral. By the way, capital S is used for surface area. So this is the surface area of one little band. And now I want the total surface area by taking the limit of a sum of the answer from the top. So follow from here and tell me what I should put inside this integral. There's a 2 pi, right, which can be pulled outside of the integral sign. What else should I have inside the integral? F of x, what else? The square root of 1 plus, which in the limiting case becomes dy over dx, right? Squared times what on the outside? Dx. So, ladies and gentlemen, that is our official formula for the surface area. And I believe it is in the handout I gave you earlier. But this kind of summarizes that one more time. Sure. So this is the formula for the surface area You see how similar this is to the arc length formula? The square root of 1 plus y prime squared. That was exactly the same thing, right? What is new here? You have an extra f of x in front, and you have an extra 2 pi in front. That's the only thing that is new here. And for this question, what was the rotation around which axis? Let's go to the top. The rotation was around the x-axis, right? Then you might wonder, okay, what if the rotation had been around the y-axis? Does the formula change a lot? Let me show you what the formula looks like if the rotation is around the y-axis. Again, this is on the bottom of your notes. So I've given you this formula on the bottom there. In general, this is what the formula looks like. 2 pi times the radius of the rotation, which I call r of x, times ds, which is the lateral side. Okay. What is the radius of rotation? If the rotation is around the x-axis, look at that figure. What is going to be the radius of the rotation? R of x will be the same as f of x. What if the rotation is around the y-axis? What will be the radius of the rotation then? R of x will be the same as just x, okay? But the formula doesn't change all that much. And how about ds? ds is the same ds from the past, which is the square root of 1 plus dy over dx quantity square, basically. So if you like, you can also add it in there, where ds is equal to the square root of 1 plus dy over dx quantity square. That's ds. Okay, so we're ready to do an example. Okay. Let's find the surface area of okay, let me find my surface area examples. One moment, please. There we go. Find the surface area of the solid generated when f of x equals x cubed is rotated around the x-axis. And I will give you a few moments to work on this.